Good morning, dear student. Last class we were discussing about the construction of root loci. We have seen three different steps. What is the first step? First step was to draw the pole zero plot. What is the second step? Existence of root locus on the real axis we computed. What is the third step? Third step is finding the breakaway point or break-in point, we call it as. Okay. So fourth step, let us understand. Before we try to understand breakaway break-in point computation, let us understand what are these breakaway and break-in points. Root locus, we don't call it as we call it as construction of root loci. What does it mean? For a given transfer function, I can call it as open loop transfer function. The number of poles or number of zeros, whichever is greater, that many root locus exist. And we know that always root locus originate from the pole and ends with a zero. Okay. If we have zeros in the transfer function, we say that root locus originate from the roots of the denominator and ends with the zeros present in the numerator. But if number of zeros doesn't match with the number of poles, then we say that root locus originate from the poles and ends with the zeros at infinity. Okay. On pole zero plot, that infinity section we cannot draw it. So we will say that the root locus keep in search of a zero to end its path. Okay. It will search the zeros at infinity and it will join there or it will end there. Okay. Now, when we have a breakaway point and break-in point, whenever we have between two poles root locus exist. I repeat, whenever we have root locus exist between the two poles, as we know that the root locus originate from the pole. So from both the poles, we will find that the root locus originate. Say take this example here. We have a pole at 0. We have a pole at -1. And we know that in this section, there exists a root locus. How can I say that? Angle condition, very simple. In this section, that is S is equal to 0 to S is equal to -1. In this section, if you identify any point P and if you calculate the angle or if you find the angle condition, then it matches with the required angle condition, then we say that in that region, root locus exists. So in this region, root locus exists, and this is also pole, this is also a pole. Then root locus originate from this pole also, and root locus originate from this pole also. Both the root locus originating from these two poles are moving here in an opposite direction. It is moving in an opposite direction. See here, from this pole, it moves in this direction. From this pole, it moves to the left. One moves to the right, the other moves to the left, and both the root locus meet at a point and it branches. Okay, and the branches will take the direction of the asymptotes and it will be keep searching for a zero at infinity. Okay, that's what the logic. So whenever we have a root locus exist between the two poles, we say that root locus originate from these two poles, meet at a point and breaks. That meeting point, we call it as breakaway point. Okay. Similarly, if you are having two zeros, then if you are having two zeros in the plot, and if you find root locus exists between these two zeros, then we say that break-in point do exist in this section. Okay. So now we will see whether root locus exists between these two zeros or not. Okay. So take any point P and try to calculate the angle condition, and it matches. Angle condition matches. So take any point in this section, it exists in the root locus, we call it as since angle condition is matching. So we say that there exists a root locus between these two zeros. You can please try out. All of you can give a try how to compute the what we call how to analyze the existence of root locus on the real axis. You can you can give a try. As we have discussed in the previous class, you please apply that concept and try to calculate whether the root locus exists in this section or not. So since angle condition matching, I'll say that root locus exists between these two zeros. What is the concept we have discussed? Always root locus originate from a pole, ends with a zero. Okay. So now root locus somewhere it will originate and ends with this zero. Again, root locus originate from some pole and ends with this zero, we call it as. The root locus originating from some other pair of poles are entering to the real axis at a point, and it branches to find their respective zeros. It branches to find their respective zeros to end its trip at k is equal to infinity. Okay, so such point where root locus meet, and branch to reach the zero, we call it as break-in point. Okay, so here we have an explanation for a breakaway point and a break-in point. Okay, so breakaway point I defined. The breakaway point corresponds to a point in the S-plane where multiple roots of the characteristic equation occur. It is the point from which the root locus branches leaves real axis and enter in the complex plane. As I said, it will move in the opposite direction, meet at a point and branches. Once it branches, it is moving away from the real axis, we call it as. That point, what we call it as break away point. Similarly, what is break-in point? The break-in point is corresponds to a point in an S-plane where multiple roots of characteristic equation occur. It is a point where the root locus branches arrives at real axis. We say that the root locus arrives, whereas in breakaway points, we found that the root locus depart. Root locus depart in the breakaway point, whereas in break-in point, we will see that root locus arrives. Okay, so now how to determine breakaway point or a break-in point? So to determine this, you have to get an expression for the gain k, and you have to differentiate that expression for k, and you have to equate that to 0. Okay, if you do that, solution to that equation is what the breakaway point and break-in point we call it as. Okay, so it should be noted that not all the solutions of dk by ds is equal to 0 corresponds to actual breakaway points. Okay, because one will be valid, the other one will be invalid. Okay, so we have to validate the points what you get. Okay, what you get by finding roots to the dk by ds equal to 0, whatever equation you get, finding roots to that equation, you will be getting some points, and you have to validate them. Valid breakaway point identification, you have to do it. How can we do whether it is a valid or not? You can apply angle condition, very simple. Or if already there exists a root locus in that section, then it is a valid breakaway point, otherwise no. Okay, so there are several techniques to declare that it is a valid or an invalid. Okay, we will see that later. Okay, if a point at which dk by ds is equal to 0 is on a root locus, it is an actual breakaway or break-in point. As I just mentioned, if it lies on the root locus, that point, you take that as a valid point. If a breakaway point or a break-in point lies outside the root locus region, then definitely you have to discard that. So that is a simple way of validating a breakaway or break-in point. Okay, or else it can be stated differently. If at a point at which dk by ds is equal to 0, the value of k takes a real positive value, then the point is an actual breakaway point or a break-in point. Okay, what is the other technique of validating that point k we have here? What is that alternate path? Once you find the roots, you have to identify the corresponding value of k. sorry, you have to identify corresponding value of k. If that k is a real positive value, then it is a valid breakaway point. Otherwise, it is an invalid breakaway point. So these are all the two methods you have to validate whether the roots you get by solving this dk by ds is equal to 0 equation. You will get many points. You have to validate them. So we have a question here for the step 4. We have one equation. This is what the transfer function we are taking for all the steps performing. So we take the same transfer function. Let us try to find the breakaway point or a break-in point. So we have g of s h of s equation. You have to construct the characteristic equation. Okay, characteristic equation you have to construct, and you have to get the equation for k. So you got a k equation something like this. K is equal to minus of s into s plus 1 into s plus 2. Differentiate this. So this, if you differentiate this, you will get the, breakaway point or a break-in point based on the pole zero plot. We have expanded this because differentiation of this is tedious. So we will expand it, get an equation in terms of s, differentiate it. You got this. Try to find the roots of this dk by ds, which is the breakaway point. So you got the two roots. This quadratic equation you can solve. You will be getting the roots as minus 0.04226 and another one is minus 1.5774. Okay. So how to, very sorry. So how to validate the 2 points? So you have to look into the pole zero plot of this, which we have plotted in the previous class. In the pole zero plot, you have to see these 2 points, whether it is lies on the root locus section or not. You have to identify. Accordingly, we will say it is a valid point or an invalid point. Okay. Since the breakaway point must lie on the root locus between 0 and minus 1, between 0 and minus 1, there exists a root locus. It has to lie in that section. Okay. Then we have a point here that is minus 0.4226. That is, it is clear that s is equal to minus 0.4226 correspond to the actual breakaway point, because this point lies in the root locus section which exists between 0 and minus 1. This is valid. Whereas this is a point where there is no root locus exist on the real axis. So you discard this and consider this. So as I mentioned, the point s is equal to minus 1.5774 is not on the root locus. Hence, this point is not an actual breakaway or a break-in point. Okay. So now you can doubly ensure it. Whatever declaration we made just now, you can go with the second technique and you can further conclude that they are valid breakaway point like this. Corresponding values of k you have to find out. Okay, so what is the k value for s is equal to minus 0.4226? Take this transfer function, substitute for s. Take the transfer function, substitute for s as minus 1.5774 and calculate the values of k. Okay, so what you get is what the k value. So I have two values. You can see that the k is positive for s is equal to minus 0.4226 and k is equal to minus 0.3849. For s is equal to minus 1.5774, it clearly says that negative values of k is not a valid point. So positive one we have to take it. So determine the breakaway point. So as I said, we have drawn the asymptotes, correct? In the previous class, we have drawn the asymptotes for the given transfer function. So now is the point of identifying the So now it's the point of identifying the breakaway point in this root locus part. So this is the root locus part. In the previous class, we have completed plotting these asymptotes. Now breakaway point, we have to identify. So this is the breakaway point. That is dark circle. What we have is a breakaway point. That is at minus 0.4226. We have a breakaway point. So that is identified. Okay, you can see here breakaway point we have identified. Now you can take a function here, k into g of s into h of s is equal to k into s minus 3 into s minus 5 divided by s plus 1 into s plus 2. So this is the equation we have. You have to construct the characteristic equation, get an expression for k, differentiate that and equate to 0. Find solution to that equation is what the breakaway point. Okay. So how to do it? This is how we are doing. K into g of s into h of s we have taken. Okay, get an expression for k, differentiate that and equate to 0. Okay, differentiate this, equate that to 0. You got 2 points. Okay, these are all called breakaway point or a break-in point. Okay, so now what I have to do. I have to validate the what we call it as actual what we call valid or invalid points. So according to pole zero map, we have 2 poles and 2 zeros. Just refer the equation g of s, h of s. This is what the equation we have. We have 2 zeros, we have 2 poles. Okay, 2 zeros, 2 poles we have. We have identified 2 poles. We have identified 2 zeros. Between 2 0, there exists what? Always break-in point. Between 2 poles, there exists breakaway point. So we have calculated here the 2 roots of the equation, minus 1.45 and 3.82. In this situation, for this particular problem, we got it as both are, valid breakaway points and break-in points we have identified and we have completed it. So now the next step, very important step, in constructing the root locus, we have to see whether the root locus crosses the imaginary axis or not. Okay, so what we have learned so far: step number 1, drawing pole zero plot. Step number 2, existence of root locus on the real axis. Step number 3, what we did, asymptotes, angles and the centroid we computed. Fourth one, what we did, breakaway point and break-in point if exist, we calculated, that is the next step. And we have the 5th step, that is determination of the point on the imaginary axis. That is whether the root locus crosses or intersect imaginary axis or not, we have to calculate. As we found that between 2 poles there exists what? Between 2 poles there exists root locus. Root locus originate from this pole as well as root locus originate from this pole. They meet and we calculated breakaway point also, and it branches. Once it branches from here, it moves away from the real axis and it takes the direction of the asymptotes. It just follows the asymptotes. Since asymptotes are crossing the imaginary axis, then definitely the root locus will cross the imaginary axis. Okay. So now from this asymptotes drawing or from this asymptotes representation, we got to know that it is crossing the imaginary axis, because asymptotes are crossing. Definitely root locus follow the asymptotes. So root locus will cross the imaginary axis. These points can be found out by Routh-Hurwitz criteria. Okay, we will use RH criteria here in calculating the what we call in calculating the crossover points, that is imaginary axis crossover point. So the characteristic equation, we took it as s cube plus 3s square plus 2s plus k, and we'll see the Routh array. If we see the Routh array for this characteristic equation, it will become like this. Routh Hurwitz in detail we have studied in the previous class, that is beginning of this module. Let us not repeat again how to construct the table. For the given characteristic equation, this is how we complete the complete the Routh Hurwitz table. Once the Routh table completes, then what we do is we'll try to guess the values for k. Okay, so you know the value of k, if it is 6, the value of k if it is 6, then it is marginally stable, we call it as. Why? Because numerator becomes 0. Okay, so it becomes 0. Immediately after that it will become negative. Correct? Any value beyond 6, if k takes, then it will become negative. Correct? So for 6 it is marginally stable. For the marginal stability point, we found that the root locus cross the imaginary axis. Okay, the crossing points on the imaginary axis can then be found by solving the auxiliary equation obtained from the s square rho, that is 3s square plus k equals 0. That is what we have to construct. 3s square plus k is equal to 0. That equation we have to construct. And for the k value, how much you have to substitute? Marginal stability value you have to substitute. What is the marginal stability here? We found that if k takes 6, this term becomes 0. Okay, any value other than that, it will become negative. Okay, so it is unstable condition. So k can take up to 6. So for 6 itself, the term becoming 0. So we have k as value 6 as a marginal stability condition that I have taken, and I try to find out the roots. If I try to find out the roots, I have plus or minus j root 2. So this is what we call it as my, root 2 is the value on the imaginary axis across which the root locus cross the imaginary axis. An alternate approach is to make s is equal to j omega. Okay, if Routh Hurwitz, if you don't want to follow, then we have another technique here. That is, you have to substitute s is equal to j omega in the characteristic equation. Both the real part and imaginary part you have to equate to 0, and then solve for omega and k. That is one procedure. You can do it. For the present system, the characteristic equation is s cube plus 3s square plus 2s plus k. Substitute s is equal to j omega. Separate imaginary terms and real terms. Equate them to 0. Equate the real part and equate the imaginary part to 0. You will get the values. You will get the values. Equating both real and imaginary parts of this equation to 0, you will get to know that 2 omega minus omega cube is equal to 0, which yields, which yields omega is equal to plus or minus root 2. Again, k minus 3 omega square is equal to 0. And here substitute omega as root 2, then you will be getting k is equal to 6. Else the other value what we have, omega equals 0 and k is equal to 0. That is the other value we have. So the complete root locus will look like this. Complete root locus of the transfer function, what we have taken for all the condition, will look like this. The dark black line you can see here. So minus 2 to minus infinity, there exists a root locus. From minus 1 to 0, we got what? The root locus existence. And this is the breakaway point. And here the root locus branches. And the branched root locus are guided by the asymptotes, as I said. And it crossed the imaginary axis at a point for which k is equal to 6. And its value found to be root 2 as we have computed. And similarly here minus root 2 we have, in which the root locus crossed the imaginary axis. Okay. Salient points on the root locus. Salient point, we look for centroid, 3 asymptotes, and poles and zeros position, breakaway point and break-in point, and imaginary axis crossover point, and corresponding k value. These are all the salient values we'll be looking for. Okay. So this is how, graphically you will look like, it will look like if you compute this using MATLAB. MATLAB is a tool we have. You can use the MATLAB to plot the, what we call root locus. You will get something like this. Okay. So I'll stop here. I'll continue with the same in the next class with a different example I'll take up. I'll continue. Okay. Thank you.